When do we say that momentum is conserved? Let us think about conservation of momentum. If one wishes to change the momentum of an object, impulse must be applied on it. This impulse must be applied on the object by something located outside the object. Internal forces, however, are not considered. Try pushing the seat of your car while it is in motion, and it doesn't affect the motion of the car at all. This is because the force you have just exerted is an internal force. Internal forces always occur in pairs, as stated in the law of interaction. They act and react within the body. Consider a rifle being fired. The force that pushes on the bullet when it is inside the rifle is equal and opposite to the force that makes the rifle recoil. These forces are internal to the system comprising the rifle and the bullet, so they don't change the momentum of the system. The momentum of the rifle, which is at rest, is zero before firing. Since momentum is a vector quantity, after firing, the momentum of the rifle cancels the momentum of the bullet. No external force acts on the system before and after firing. This means that no impulse is present to change the momentum of the system. Momentum is said to be conserved. Consider a box as our system. Inside the box are a gun and a bullet. If at this moment the box is at rest, then the momentum of the box is zero. If the box is pushed sideward, the momentum is changed. But if the box remains at rest and the gun fires the bullet, still the momentum of the box is zero. Thus we can conclude that the momentum of the body in the absence of an external force before and after firing remains unchanged. In the absence of external force, the momentum of a system remains unchanged. This is the law of conservation of momentum. When cars collide, when nuclei decay and when stars explode, the net momentum before and after the event is the same. An explosion is actually a consequence of Newton's third law of motion. Since no external force is applied on the bomb, then the momentum of the bomb is conserved. The law of conservation of momentum applies to objects in collision. In some collisions, two objects collide and stick together so that they travel together after the impact. An example of this is the collision between an arrow and a target. The arrow sailing forward collides with the target at rest. In an isolated system, the arrow and the target would both move together after the collision with a momentum equal to their combined momentum before the collision. Here let's take a closer look at the combined momentum of the truck and the car before and after collision. When two objects collide and move together as one mass with the same velocity, like the arrow and the target, the collision is called perfectly inelastic collision. In symbols, m sub 1 times v sub 1 plus m sub 2 times v sub 2 equals the quantity m sub 1 plus m sub 2 times v sub 3, where m sub 1 and m sub 2 are masses of objects, v sub 1 and v sub 2 are initial velocities of objects, and v sub 3 is the common final velocity with which the objects move. Let us explore sample problem 1. A 1,850 kg van stopped at a traffic light is struck from the rear by a 975 kg car. The two vehicles become entangled as a result of the collision. If the car was moving at a velocity of 22.0 meters per second to the north before collision, what is the velocity of the entangled vehicles after collision? And here are the given quantities, the required quantity, and the equation or formula that can be used to carry out the solution to the problem. By utilizing the formula previously provided, Here's the solution, and the answer to the given problem. In an elastic collision, two objects collide and return to their original shapes without change in total kinetic energy. After the collision, the two objects move separately. In this type of collision, both the total momentum and the total kinetic energy remain constant. In symbols, m sub 1 times v sub 1 initial plus m sub 2 times v sub 2 initial equals m sub 1 times v sub 1 final plus m sub 2 times v sub 2 final, where m sub 1 and m sub 2 are masses of objects, v sub 1I and v sub 2I are initial velocities of objects, and v sub 1f and v sub 2f are the final velocities with which the objects move separately. And now let's have sample problem 2. A 0.025 kilogram marble moving to the right at 0.225 meter per second makes an elastic head-on collision with a 0.035 kilogram shooting marble moving to the left at 0.180 meter per second. What is the velocity of the shooter marble after collision if the smaller marble moves to the left at 0.315 meter per second? And here are the given quantities, the required quantity, and the equation or formula that can be used to carry out the solution to the problem. By utilizing the formula previously provided, here's the solution and the answer to the given problem. Let's summarize. The momentum of a system is conserved if no external force acts on it. Conservation of momentum is also applicable in elastic and inelastic collisions. And here's your self-activity 1, perfectly inelastic collision. A 48 kilogram student runs down the sidewalk and jumps with the horizontal speed of 4.00 meter per second onto a stationary skateboard. The student and the skateboard move down the sidewalk with the speed of 3.50 meter per second. Find the following. Letter A, the mass of the skateboard. Letter B, how fast the student would have jumped to have a final speed of 5.00 meter per second. Self-activity 2, elastic collision. Number 1. A 5.0 kilogram bowling ball, moving to the right at 8.0 meter per second, has an elastic head-on collision with another 5.0 kilogram bowling ball initially at rest. If the first ball stops, what is the velocity of the second ball after collision? Number 2. A 25 kilogram bumper car, moving to the right at 6.0 meter per second, bumps elastically from behind a 35 kilogram bumper car moving to the right at 3.0 meter per second. What is the velocity of the heavier bumper car after collision if the lighter bumper car slows to 1.5 meter per second? Again, thank you for taking time to learn. May you be guided with force and motion to move along and learn to a positive direction, possessing the energy and the power to work overtime while studying the hardest way you can.